Hello and welcome back to another LeetCode video. We're looking at LeetCode 3375, minimum operations to make array values equal to k. And it's an easy problem, and you might wonder, why would somebody make a video about a LeetCode easy problem? Well, I'm using these easy problems to practice the interview process. They don't get in the way of the process, and I can focus on communications, thought process, and just dialing in the system that I need, that I would need in an interview. And the first step is to actually read the problem description. So let's do that. So we are given an integer array nums and an integer k. All right. An integer h is called valid if all values in the array that are strictly greater than h are identical. Interesting. For example, if nums is 10, 8, 10, and 8, a valid integer is h equal 9, because all numbers, excuse me, larger than 9 are equal to 10. But 5 is not a valid number, because, why not? All of the values are strictly greater than h are identical, because, well, 8 and 10 are greater than 5, but they're not identical. So 5 is not a valid number. I get it. So you're allowed to perform the following operation on nums, on the array nums. Select an integer h that is valid for the current values in nums. For each index I where nums at position I is larger than h, set nums I equal to h. Interesting. Return the minimum number of operations required to make every element in nums equal to k. If it is impossible to make all elements equal to k, return -1. So I now want to, in an interview, I would now ask about, okay, well, is nums can nums be empty? Does it always contain elements? What are the values that I can expect in nums? Can I get a null reference here or something? And likewise, what are the values for k? So in LeetCode, they tell us that on the bottom here. So we see that the nums array contains at least one element, and all the values are positive integers larger than 0, and k is also a positive integer larger than 0. Cool. All right. So to get a better intuition, because I don't have a full intuition right now how to solve this. So the antidote to that situation is to actually look at an example. Either ask the interviewer for an example or make one up yourself. On LeetCode, we give an examples, which is nice. So let's look at example 1, where we have nums equals 5, 2, 5, 4, and 5, and k is 2. All right, so I have to remind myself. Second. Okay, what was k again? Return the minimum number of operations required to make every element in nums equal to k. Okay, so k is kind of like a lower bound. So I guess if nums contains elements that are smaller than k, then we can't do anything. Yeah, here, there's an example. 1 is smaller than k, we can't do anything. Because we're not making numbers larger, we're only making them smaller, right? Where nums at position I is larger than h, we can set it to h. So we cannot make smaller numbers larger. So in that case, we have to return -1. So I guess I would add this as an edge case in a second. But that's maybe the first insight from example 2. Okay, let's go back to example 1. So what do we do here? Well, so I guess we should start at the largest numbers, right? So we have 5, 5, 5. They're all the same. So I would now check 4. No, what can I do with 4? Select an integer 8 that is valid for the current values in nums. So when was h valid? An integer 8 is called valid if all values in the array are strictly greater than, if all values in the array that are strictly greater are identical. So it's fine if I pick a number for h that already exists in the array. It's only that the ones that are larger must all be the same. Nice. Yeah, so in that case, I can do that. I can replace all the 5s with 4s. Right, so let's do that. So yeah, we would replace the 5s with 4s. And I think it would be easier if we sorted them first. 5, 5, 5. So let's do the sorting. And maybe that's something we have to do in the solution as well. So We have 5, 5, 5. We pick h as 4, and we replace the 5s with 4, right? Next, what do we do now? Well, we can pick, we have to pick a number that is smaller than the largest number. The largest number is now 4. So if we pick 3, we could make all the 4s equal to 3, right? H is equal to 3. However, we could have also just picked 2 because 3 is not used, right? So now we have, this is where we apply this one time, and this is where we apply this another time, this technique. So that's why the output is 2. Okay. Let's try this example down here. And we'll do sorting so that we have 3, 5, 7, and 9. And now we can pick for h. Oh, I get it now. So what we do is we have to pick, well, I suppose it's always going to be possible, you know, as long as the numbers are larger than k, we can always do that because we just have to pick the next number that is smaller than the largest number. So in this case, we pick the 7. So we just say h is equal to 7 because all numbers larger than 7 are the same. It's only a 9. So what we end up with is 3, 5, 7, 7. Now we do the same thing. So the next smallest number that is not in the array, the next smaller number that is also in the array is 5. So now we pick 5. Let's remember what k is. K is 1, right? So here k is 1. So we want to go to k, but here k was 2, right? So that's why we terminated when everything was 2. Right, so now we pick h5. We set the 2 7s equal to 5. Now again, we have to pick the next number that is smaller than the largest number there. In this case, it's 7. 3. And now we make everything equal to 3. And now, well, we can pick any number now, right? We could say h is 1. So I guess if all elements are the same in the array, and they're not k, we select our h to be equal to k. That is 1. And then we get an array of only 1s. So in this case, we've performed this one time here. We have performed this another time here. And here. So I think the result should be 4 in this case. Yeah, and that's exactly what it is. Cool. So I think we've understood the problem. And let's think about this approach. What is the worst runtime complexity? Well, the worst case is if all the numbers in the array are strictly increasing, so they're all different, and they all differ by 1, and our k is equal to the smallest value minus 1 in the array. In that case, we have we have to do this operation O of n times, right? And in terms of space, we can reuse the space in nums. But every time we would have to iterate over the numbers and change them. So yeah, it's going to be an O of n squared time and O of 1 space approach if we did that. And I want to think a little bit more about this. Maybe we could also simplify this a little bit. So can we determine that somehow from the number of different values that we have in the array? Right, because so here we have 1, 2, 3 different values. And if we add 3 different values, so we know we have to perform this operation once to reduce it to 2 different values. We know we have to perform it twice to reduce it to 1 different value. Means all are the same. Yeah, that looks like we just have to count how many different values there are. We have 3 different values. 1 minus 3 is 2, and that's our result here. So let's look at this example. So here we have 4 different values. But also k is also a different value. So I suppose, yeah, we have to count k towards the different values in the array. So here, since k is in the array, it's still only 3 different values. So we return 3 minus 1, which is 2. Now we have 5 different values if we count k1, so we return 5 minus 1, which is 4. Awesome. So I think we just found another way of how we can solve this problem, and that would be in O of n time. And O of 1 space, I would say. Okay, but this assumes that all the numbers are sorted. That's what that assumes. So I guess there's a trade-off here. Well, we could use a hash map, I suppose. Or just a set. But that would also require n space. So now we have 2 different approaches, as a quadratic one that has constant space and a linear one that requires linear space, right? And in an interview, I would ask the interviewer, okay, which one do you want me to implement? And let's say the interviewer says, okay, let's implement the one with linear, that has the better runtime. But talking about these trade-offs is really important, you know? Just because the runtime is shorter doesn't mean it's the better algorithm. It uses space. This one doesn't, you know? So, but let's implement that one. It's also less typing than the other one, so that's what I'm going to do. Right, so, well, first we have to determine what is the number of distinct elements in nums. Well, we're just going to create nums is equal to the set of nums. So we remove all duplicate numbers. And then we're going to add our k to it. Now, we need to perform a check. Remember the edge case? So if k is smaller than, if the minimum in nums is smaller than k, return minus 1, and there is no solution. That's the edge case. And otherwise, well, we have our set, and we just return length of nums minus 1. That is the result, right? So, and in the best case, all the numbers are already equal to k. So that means the length is going to be 1 minus 1. We have to do 0 steps. So let's test this solution. If it works as beautifully as we stumbled across it, and it seems to do exactly that. But let's now see if it passes all of the tests. Very nice. So it passed, and we found, I would guess, the optimal solution as well. So that concludes this little video. And by the way, this is a good example as for why practicing easy problems is really useful. You know, it would take much longer and with a medium problem to maybe see 2 different approaches and be able to reason through that. So that's why I would always recommend do easy problems to practice the process. And when you run into a scenario like this in a medium problem, which might not occur as often because they take longer, you are prepared.